Hello friends, today we are going to discuss one of the important sub-theme in biomolecules about carbohydrates, its classification and structures. You know, carbohydrates. Carbohydrates are the most important abundant organic molecules in nature. What are carbohydrates? They are nothing but polyhydroxyaldehydes or ketones or compounds which produce them on hydrolysis. And we all knew that they are the abundant dietary source of energy, say 4 calories per gram. Carbohydrates in the form of glycoproteins and glycolipids serve as important structural components in cell membrane and also aids in cellular functions like cell growth, fusion and fertilization. And carbohydrates also serve as the important precursors for other organic compounds like proteins. Okay, today in this class we will discuss about the classification. Most important is stereoisomerism of monosaccharides. That means different structures related to monosaccharides. And these are all very important in examination point of view. At the same time, in research point of view as well. Okay. First of all, as we have discussed, they are nothing but polyhydroxy aldehydes or ketones. With respect to the classification, based on the number of units, one or few or many, this convention, as we all knew, that carbohydrates are divided into monosaccharides. Here carbohydrates is regard to saccharides, that means sugars. Oligosaccharides, polysaccharides. Monosaccharides based on the functional group. Mono is simply, it implied one unit. Based on the functional group, again there are two kinds: aldoses, ketoses. Say for instance aldoses and ketoses. Based on the number, say trioses, 3 carbons, tetroses, 4 carbon, pentoses, hexoses, heptoses. That means 5 carbon, 6 carbon and 7 carbon. Oligosaccharides, say based on the number di, tri, etc. Poly are again of homo and heteropolysaccharides. Monosaccharides, observing and studying the structures of monosaccharides are important because it enables us to understand different oligosaccharides and polysaccharides as well. Trioses, for example, glyceraldehyde 3-phosphate, simply called GAP. Glyceraldehyde 3-phosphates, dihydroxyacetone. But these two are one of the important intermediaries in glycolysis. Tetroses, say D-erythrose. Its phosphate form is an important intermediary in carbohydrate metabolism. Pentoses, say D-ribose. Of course, we all knew that an important component in RNA, and 2-deoxyribose in DNA, of course. Likewise, hexoses, D-glucose. Of course, the sugar fuel, the energy currency, it's ATP, And regarding oligosaccharides, we have sucroses, for example, maltoses, and lactose. Homopolysaccharides simply can starch, and it is mucopolysaccharides. It's just brief overview of classification of carbohydrates. Then the most important theme is structural, as we told, as we have to discuss in the examination, the center in analysis point of view. The structures are very important. Of course, in any biochemistry chapter, without structures, one could not possibly understand different issues related to it. Okay. In order to understand structures, we have to understand stereoisomerism. You know, stereoisomerism. Here, compounds are stereoisomers having same structural formulae, but different spatial configuration. To understand different structures like optical isomers, apimers, enantiomers, enamers, or mutarotation, we have to understand stereoisomers. All these different sub-themes, that means structural aspects of monosaccharides, come under the head of stereoisomerism. As we have discussed, it is nothing but having same structural formula but different spatial configuration with respect to different groups. How it established? The crux point of this issue is asymmetric carbon. Asymmetric carbon. What is an asymmetric carbon? If a carbon attaches to 4 different atoms or groups, 4 different atoms or groups is an asymmetric carbon. This asymmetric carbon leads to isomers. That means if there are different, at least one asymmetric carbon should be there. That leads to isomers. We'll discuss what exactly and how it comes, okay? How we establish isomers depends on the number of asymmetric carbons. It is represented by a simple mathematical formula like 2 to the power of n. In glucose, for example, there are 4 asymmetric carbons. Take for example of glucose. 2 to the power of 4, that is 16 isomers. That means based on the number of asymmetric carbons, one could easily or possibly understand and establish the number of isomers. Just like glucose 2 to the power of 4 to 16. That's how the issue ends. But here the entire scenario of structural, the variety of structures of monosaccharides come under stereoisomerism. So one have to understand this concept to go, that means for further discussion. Right? Then here glyceraldehyde is considered as a reference carbohydrate. Glyceraldehyde is an aldose. Why it's called reference? Because based on the glyceraldehyde, each and every structural component will come glyceraldehyde. Its structure is very simple. It is a reference compound. It is aldotriose. Glyceraldehyde is an aldotriose. It is called reference compound because entire structures, that means the positive, we already told stereoisomers is a variation of spatial configuration. That means possible isomers, possible configurations are entirely depend on this structure, that is this reference compound, what we call glyceraldehyde. How? We'll draw one by one. The structures are understand, for how it established or leads to different structures. Stereochemistry is all about organic chemistry, and we have to understand different things for proper conduciveness. Say the reference compound glyceraldehyde. This is aldotriose. That is 3 carbon. That leads to again 2. This D-erythrose and it is D-threose. D-threose. These are tetroses, 4 carbons. Again from D-erythrose, 2 compounds will come. This is D-ribose, is D-arabinose. From here again 2 compounds. This is D-xylose. And this is another one. This is D-lixose. These are aldopentoses. Aldopentoses. 5 carbons. Then it's again 2. This is D-allose. D-allose. This is D-altrose. It will form 2. This is D-glucose. And this is D-mannose. Again form 2. This is D-gallose. Again will other one come. This is D-iodose. Again it will form 2. This is D-galactose. And final product. This is D-talose. You know, they are the possible configurations. I told you already. Glyceraldehyde, from this glyceraldehyde reference compound, how they say aldotetroses, D-hydrose and D-threose, aldopentoses, D-ribose, D-arabinose, D-xylose, D-lyxoses, and aldohexoses, 6 carbons. That means D-aldose, D-altrose, D-glucose, D-mannose, D-glucose, D-idose, D-galactose, and D-talose. I told you already. Reference compound means it is a basic compound from which the other compounds will come. I told you simple. Stereochemistry means the variation in spatial configuration. Spatial configuration. Here, it needs to add the addition of one extra chain. One extra chain each time. Just say this 2 carbon, one extra chain you have to add. Just to understand, only one extra chain. This is 4. And one extra chain. This is 5. And one extra chain. This is 6. Based on it, the second compound in reverse. Addition of one extra chain. How? Simply spatial configuration. That's how the issue ends. That is why the glyceraldehyde is the reference compound. So we must be very clear. Stereochemistry is the base for all. Then let us take an example of glucose. That means which is one of the important monosaccharide for understanding different structures. So it's all about how the groups, that means HOH groups, you must be clear about, how they differ because of HOH arrangement, what we call simply. The HOH arrangement is the basis for each and every structure of carbohydrate. Say whether it is right, if it is right side, it is one form. If it is on left side, it is another form. That is how they form different compounds. What I mean to say is, for example, under the head of, say, who takes glucose, different words we have structural aspects of glucose. Structural aspects. In different heads, optical isomers, epimers, enantiomers, enamers. That means mutarotation. Optical isomers, first of all, optical isomers. T and L forms based on spatial configuration and one carbon atom. That means C5 in case of glucose. How it established? D and L form is dextrose D or right side. Right side. L levo or left side. What is right and left side? If the OH group is on right side, it is dextro. That means the entire concept depends on the OH group. If it is right side, D. If it is left side, L. Dextro rotatory form, levo rotatory form. How it established? Just you pass a beam of light through a solution of optical isomers, and this light may rotate either to right side or to left side. D form, L form, like this. That is how they establish. And how that means that simply mirror images. For example, how they deform. So no, depends on OH group entirely. The simple concept, the simple logic, the simple hint. If it is on right side OH group, deform. If it is on left side, but on a one particular carbon atom. It depends on one carbon atom. For example, C5 in case of glucose. That means if the OH group in case of glucose at fifth carbon on right side, it is D form. If it is left side, L form. That's it. For example, how we know, we'll draw how it comes to an end. This is D glucose. Then this is L glucose. I told you fifth carbon. This is fifth carbon. OH group. The how we have to determine that glucose is in D form or L form? Just observe the fifth carbon. If the hydroxyl group on right side, then it is D form. The left side, L form. That's it. They are simply mirror images. I told you already. Variation, that means differential spatial configuration, is the basis for stereoisomers. And these are optical isomers. Okay. Then the second component, epimers. Epimers are similar to that, but there is one change. In epimers, actually, there are differences among different monosaccharides based on the spatial configuration around one particular carbon atom. It is how, for example, take one example of D-glucose, D-galactose, and D-mannose. We'll draw how they differ, what we call epimers. Say first D-glucose, this is the basis, This is D-glucose. Okay, this is D-glucose. I told you already, one particular carbon is the basis for variation, With respect to D-glucose and D-galactose, it is C4. And with respect to D-glucose and D-mannose, it is C2. For example, then it is D-glucose and D-galactose will draw. Entire structure is same except at one particular component. I told you already. At around one particular carbon, that there is a change in spatial configuration. D4. That's it. The rest is same. C4. Just observe in C4, in D-glucose, the hydroxyl group is on right side, but in case of D-galactose, it is left side. These are epimers. Just variation in spatial configuration, means OH and H group. This is very important. The basis for all the spatial configuration is the arrangement of OH and H group only. That is simply OH group. A is at C4. Say D-mannose. Entire structure is similar, I told you already, except one particular carbon that leads to formation of epimers. This is D-mannose. I told you C2. This is C2. This is C2. The change. The hydroxyl group in D-glucose right side, D minus on left side, that's it. They're epimers. Variation based on one particular carbon atom. Then the enantiomers. Enantiomers is similar to the optical isomers only, but the thing is they are specialized form of stereoisomers and they are non-superimposable mirror images. How it ends? Say they are same D and L forms only. Say take example of glucose. This is D form, D glucose. This is L glucose. The same, but they form non-superimposable mirror images. That's the only, that means specialized type of stereoisomers. That's it. The same comes, but that's a certain difference in the right side, the left side. For example, because they are mirror images. Mirror images. They are called enantiomers, enantiomers. And last important structural component, enantiomers are mutarotation. You must be knowing the entire scenario depends on the variation in spatial configuration. That's it. If you know the logic, how to incorporate the different H and OH based on specific carbon atom, say for example C5, if let's put optical all isomers, and C4, just put epimers, and C1 next enantiomers, it is very easy. And understanding the basic concept of stereochemistry is very much essential for drawing the different structures. That means structural aspects of monosaccharide. This is very important. Even examination point of view, they will ask you which carbon is basis. For example, apimer C4 between glucose and galactose, and C2 in case of glucose and mannose. Glucose and mannose. It is very important. One have to understand the logics. Okay. Then the enantiomers. Last compound. Enantiomers. Enantiomers nothing but there are the beta alpha and beta cyclic forms of D-glucose. There are two projections. Actually, Fisher hypothesis is very prominent. At the same time, Haworth projection. Haworth projection actually presents two forms, pyranose and furanose forms. Generally, we follow Fisher projection because of time constraint. We will take an example. How we construct alpha and beta cyclic forms of D-glucose. Same, first you need to draw a D-glucose. I told you already, if you understand the logic, the concept is very simple. If you don't understand the logic, it is a juggernaut. So, understanding logic is important. This D-glucose, we all knew that. Then its alpha form with respect to Fisher, we are discussing about Fisher hypothesis, Fisher projection, what we call, how it comes in, Then the alpha, that means it's called alpha D glucose. Then its opposite form, the beta D glucose. I told you already, here the spatial configuration variation is based on C1 carbon in case of glucose. So one carbon is the basis for variational spatial arrangement. C4 with respect to epimers, C5 with respect to optical isomer. That means in case of optical isomer, C5 carbon variation, that means HOH adjust arrangement in case of optical isomers. Whereas in case of epimers, it is C4 based between D glucose and D galactose, and C2 between D glucose and D mannose. Likewise, in case of enamers, it is C1. That means the production, the alpha and beta cyclic forms based on a projection based on one particular carbon, the C1, enamers, what we call enamers, and they based on Fischer projection. For example, here the C1, the entire compound will be same. This is the basis. C1, I told you already, C1. This is reverse. This is how the issue ends. Enamers. The crux point is same, the spatial variation. That is why I am stressing this point. Next, these are about monosaccharides. Next, the important, we are not going to deep about just we are learning some basics how the bond pattern forms in case of all the disaccharides. Say, take the example of sucrose, disaccharides. Say sucrose, then maltose, then lactose. We all know that sucrose contains alpha D glucose and beta D fructose. Same this representation, I'm giving for better understanding how the bonding pattern will form here. One and 4. That means 1 and 2. Alpha 1 to beta 2 glycosidic linkages. The two units linked by alpha 1, that means alpha 1 beta 2 glycosidic bond, the bonding pattern. Say the maltose, simply 2 glucose, 2 alpha D glucose units. Concept is same and simple. One 4, that means alpha 1 4 glycosidic bond. This is very important. Then lactose, this is a bit different. It's beta D galactose plus beta D glucose. Say fine, it's the same concept but the beta form or the alpha. You can see the kind of arrangement of beta 1 4 glycosidic linkages. That means glycosidic bonds, we all knew that. Is that basics? I'm not going to the basics. We all knew that glycosidic bonds connects different subunits. For example, in case of monos or disaccharides, say sucrose, alpha 1 to beta 2 glycosidic between alpha D glucose and beta 2. Maltose 2 alpha D glucose simply by alpha 1 4 glycosidic linkages, and lactose beta 1 4 glycosidic bonds. In case of polysaccharides, see, a bonding pattern is very important. Bonding pattern is very important because in most of the exams they will ask you the kind of bond. polysaccharides. They are homo and heteropolysaccharides. The best example for homo is starch. It exists in two forms, amylose and amylopectin. Heteroid is nothing but a mucopolysaccharides. Example, in case of amylose, the monomer units held together by alpha 1,4 glycosidic bonds and it is linear. It is, in case of amylose, it is actually it is soluble. Whereas amylopectin is insoluble and it is a branched one. That means, say for instance, and it linked by alpha 1 to 6 glycosidic linkages at branches at rest and alpha 1,4 glycosidic in linear fashion. This is all, for example, this is amylose, alpha 1,4 glycosidic linkages, simply alpha 1,4, and and this is same here, but the thing is at branches this is a different pattern. This is alpha 1,6 glycosidic linkages at branches. This is very important in case of amylopectin. In case of linear elements, it is quite similar. This like, that means, say for example, the individual monomers will link by alpha 1,4 in case of linear, but at branches it is alpha 1,6 with respect to amylopectin, because amylopectin is a branched polymer, amylose is a normal polymer. When say alpha amylase, why it is considered as alpha amylase? Because alpha amylase is an enzyme that breaks down the alpha 1,4 glycosidic linkages. This one, that break down alpha 1,4 glycosidic linkages between different monomeric units of a starch. Say for instance amylose, that leads to the dextrins. Say the starch leads to dextrins, that means the breakdown product of starch, then it leads to maltoses, then ultimately leads to glucose. That means dextrin for first form, the maltose, then glucose. That's how they release. So it's about different structural aspects, the stereochemistry I told you already, of different monosaccharides and other issues, structural aspects of disaccharides and polysaccharides were discussed an examination point of view. I told you already it is very important. The main objective of my presentation is for poor and talented students. Okay, you can like and comment, share. Thanks for watching.